Hello, so welcome to the probably the last lecture of group theory, and we'll continue from where we left. So we are discussing homomorphism. In this lecture, we are going to discuss isomorphisms, but the last result of homomorphism part, which was remaining, uh, which was this result. So that lemma we were discussing, and this was the lemma. If you recall, we are left with the statement. The proof was remaining, and we had discussed one example. So the lemma was this: if phi is a homomorphism, if phi is a homomorphism of G in onto of G onto some group G bar with kernel K, with kernel, suppose we denote the kernel by K, then we are interested in investigating what are all the inverse images of some element of G bar. So then the result is this: then the set of all inverse images then the set of all inverse images of some element of some G bar in this G bar under phi, inverse image under phi. So inverse image will be in the domain. So in G is given by kx. It is given by kx, where what is x? X is one particular inverse image of G bar. So where x is any particular inverse image of G bar in G. So if G bar equals to identity E bar, then we know it is inverse image is nothing but the set kernel, which is by definition. But if we take arbitrary element G bar, then we cannot always find out the set of inverse images. But if we know one particular inverse image, say x is the inverse image of G bar, that means phi of x equals to G bar, then we can find all using the kernel. So the set is nothing but it is kx. Right, and we have seen one example also of this one in the last video at the end. And so now let us complete the proof of this. So we have to show that any inverse image of G bar is nothing but kx. So first of all, we show that all the elements of kx are inverse image of G bar, and if there is any inverse image of G bar, it is in kx. So right, two things. First, kx के जितने element है वो they are inverse image of G bar. That is the first. And you take any inverse image of G bar, it must be in kx. So combining these two facts, we can say that it is exactly the elements of kx. So what we do is let y belongs to kx. Right? So we want to show that every element of kx is inverse image of G bar. So y is inverse image of G bar. That means we want to show that phi of y is equals to G bar. So let y belongs to kx. So then y can be written as small kx for some k in k. What is k for us? K is kernel for k in k. And then what is phi of y? Phi of y is same as phi of kx. Because phi is homomorphism, this is phi of k, phi of x. And what is phi of k? K is in the kernel, so phi of k is E bar. What is phi of x? X is one particular inverse image of G bar. That means phi of x is nothing but it is G bar. And what is this? This G bar. So phi of y equals to g bar, that means y is inverse image, thus y is inverse image of g bar. Y is inverse image of g bar in G under the map phi. Right? So we started with the arbitrary element of kx, and it is inverse image of this. So all the elements of kx are inverse images of uh, g bar. Now what we need to show is, if there is any other inverse image, then it must be in kx. So assume that z uh, is inverse image of, so suppose z is an inverse image of g bar under phi. So that is phi of z equals to g bar. But we already know x is a particular inverse image of g bar. That means, but phi of x is also g bar. So that means, hence we have phi of z equals to phi of x. And what we do is we multiply by phi of x inverse both sides. So phi of x inverse. And this is e bar. Right? So x was one particular inverse image. Z is any inverse image we have. So we have this. But phi is homomorphism, and yesterday we have seen this phi of z. What is phi of x inverse? This is phi of x inverse. Right? Inverse of phi of x is same as phi of x inverse. And again, phi is homomorphism. So this is nothing but phi of z x inverse equals to e bar. So this element zx inverse, the image is e bar. That means this belongs to the kernel. Very simple, yes. So that means zx inverse belongs to kernel of phi because it is mapped to e bar. Kernel of phi is nothing but k. Zx inverse belongs to k multiplied by x on the right hand side. So we have, this implies z belongs to kx. So these are the two things we have done. What are the two things? First, this one, y belongs to kx, and what we have seen is phi of y equals to g bar. That is the first thing, and this is the second thing. You take any z in G such that phi of z equals to g bar, that is z is inverse image of g bar. Then what we have obtained here is z belongs to kx. Right? So this completes the proof of the lemma. I hope this is clear to you. You can repeat it, and if you have doubt, you can ask. We already discussed this in the last class. So, right. Okay, now we come to the next topic, which is again in the subtopic of this, which is isomorphism. Again, this is revision part for almost all of you. When we say that a map is isomorphism, so a homomorphism suppose we have homomorphism phi from G from a group G into a group G bar. So a homomorphism from a group G into a group G bar is said to be isomorphism. Is said to be an isomorphism if phi is 1, 1. That is, kernel of phi is singleton identity. So if phi is 1, 1, then such a homomorphism is called isomorphism. So we have discussed all the examples of homomorphism in the last lecture. That is why I asked you to find out how many are 1-1, how many are not 1-1. So you have first of all examples of homomorphism. You can find which one of them will be isomorphism. Right, when we say that two groups are isomorphic, so two groups G and G bar are said to be isomorphic if there is an isomorphism, that means 1-1 homomorphism from G onto, this is important, G onto G bar. Right? So there is isomorphism from G onto G bar. So isomorphism onto isomorphism. Isomorphism, that means already homomorphism, and 1-1 that was already there. So this is isomorphism from G onto G bar. So it is 1-1 onto and homomorphism. Then we say that G and G bar are isomorphic. For isomorphism, only 1-1 and homomorphism. Two groups are said to be isomorphic if there is an onto isomorphism, not into. Right, so you can now find out those examples which two groups are isomorphic in the above examples, and you can also consider more examples. And the exercise which I had given in the Google Meet class is this, that being isomorphic to or group isomorphism is an equivalence relation. So show the following. If suppose we have three groups G1, G2 and G3 are three groups, then so we have the following. G1 is isomorphic to G2. Okay, so here we have forgotten the notation. So we denote by so isomorphism is denoted by this. G is this is the symbol. There are many other symbols also, but the one used here is this. G is isomorphic to G bar. And what we have to show here is this is an equivalence relation. So G1 is isomorphic to G1. Second, if G1 is isomorphic to G2, then G2 is isomorphic to G1. So this is symmetric. And third is transitivity. So if G1 is isomorphic to G2 and G2 is isomorphic to G3, then G1 is isomorphic to G3. Right, so this one was the exercise given to you. And finally, in this topic, the most important theorem. Again, this is a revision which you already studied, and so this one is called the first isomorphism theorem. So this proof also is an exercise, easy exercise now. We already studied in B.Sc. So before I write the statement, so let me first write the statement and give you a hint. So if phi is a homomorphism, if phi is a homomorphism from G onto G bar, onto is there here, with kernel K. So phi is onto homomorphism from group G to G bar with kernel K. Then we have to prove that G quotient K The domain quotient, the kernel, is isomorphic to the image. Image here it is G bar because it is onto. So onto is important. If we don't assume onto here, this will be replaced by phi of G, the image. So domain quotient, the kernel, is isomorphic to the image of the homomorphism. But here we have onto, so we just take G bar. So we have G bar here, right? And the hint is this, that we have seen kernel is always a normal subgroup, and if G is a group and N is normal subgroup, G to G quotient N we are defined, X going to NX. So we have a map here, G and G to G quotient K. This is a map G to G quotient K. This is sigma. And there is an onto homomorphism where we are given that the map is phi, that is G to G bar. So what we want is we must have a map from this psi. And what will be this map? This map is so element of G. So element of G, suppose I take G, then how is phi defined? G is mapped to phi of G. And how is this defined? G to G quotient K. So G to G quotient N, we know N is normal subgroup. There is a homomorphism G from G to G quotient N, defined by phi of X equals to NX. So this is G and G quotient K. So it is right coset KG. So we must have a homomorphism which maps KG to, so this is the hint which we get actually from the this idea, that how do we define the homomorphism from C? We want to show that these two are isomorphic. So how do we do this? So we need an homomorphism from G quotient K to G bar. How do we get? So using this two homomorphism, we get here, this is the one which is psi, and this one is phi, this one is sigma. So sigma G equals to Kg, right? So define this, the idea will be to define psi from G quotient K to G bar by psi of, now what is an element of G quotient K? It's a coset. So coset of K in G. So it is something like this, Kg. And once we have Kg, where do we define map Kg? The idea is to define Kg to phi of G. Then the exercise is, this was left as exercise because I know you have already seen this in B.Sc. This is just a revision part. So we're not going to discuss all the topics here in detail. So this one we have to show that psi is well defined. 1 we want to show that G quotient K is isomorphic to G bar. So isomorphic means 1 onto homomorphism. So these are the things we want to show. So that is left as exercise, well defined 1 onto homomorphism, using the fact that what we are given, on the other hand, we are given that phi is a homomorphism of G onto G bar. So using the fact that this G to G bar, phi from G to G bar is an onto homomorphism. So this much we are given, right? All right. So this completes the section on isomorphism, and then the last result which remains, which is a very important result, which is Cauchy's theorem. Now before going to Cauchy's theorem, so this is the last section. So before going to this theorem, I'll give you two easy exercises. Again, this you may have already done. So first one is so let G be a group. Let G be a group. If G has no proper subgroup, then if G has no proper subgroups, if G has no proper subgroup, then G is a cyclic group of prime order. So we consider here maybe finite group. Let us consider finite group. So suppose G is a finite group. If G has no proper subgroup, then G must be a cyclic group. Not only that, its order must be a prime number. So if G has no proper subgroup, then G is a cyclic group of prime order. This is a first exercise, very easy. Try it yourself, especially those who are interested in problem solving. Right. Second exercise, this you all must have done in B.Sc, and we already know that it's a very trivial exercise. Just applying division algorithm. I'm giving you the hint also. So let G be a group. This we have used so many times, but we hardly prove it. So let G be a group and A belongs to G. With order of an element we know smallest positive integer such that A raised to n equals to identity, then we say that n is the order of G. So A raised to n equals to identity, and n is the smallest positive such integer. So order of A equals to n. So this much is given. And if order of m, if A raised to m equals to identity, then what is the relation between n and m? Of course, by definition, n is the order, so n is the smallest integer, such that A raised to n equals to identity. So of course, n is less than equals to m. That much we know. But what more we can tell is that n order divides m. So that is order of A divides m. So it is not just the smallest, but whatever the power A raised to m equals to identity, the order of A must divide that power m. Right. So this are the two exercises, and now we come to the important result, that is called Cauchy's theorem. But we are not proving here for in general. We are proving for finite abelian groups. So Cauchy's theorem, and this is a special case for finite so this is a special case. We are proving for finite abelian groups. It's not just arbitrary group. In the second unit, we'll prove the result for arbitrary, in general, any finite group. So what is Cauchy's theorem? Let of course we are taking finite abelian group. Let G be a finite abelian group and P be a prime such that, so G is a finite abelian group and P be a prime such that P divides order of G. So we take a finite abelian group and a prime dividing order of G. Then what Cauchy's theorem says that then there is an element A in G, and A is not equals to E such that a raised to p equals to identity. So there is an element, non-trivial element, such that a raised to p is identity. Now, what does this mean? So we are considering the case for finite abelian groups. We'll prove in the second unit later for general case, any finite group, but right now we are considering the abelian case. So G is a finite abelian group and P is a prime dividing order of G. This much we are given. So there is a prime dividing order of G where G is finite abelian group. Then what this result says, there is an element in G, non-trivial element, so that is other than identity. There is A in G not equals to E, such that A power P, this prime, A power P equals to identity. So what does this mean? From the above second exercise, as you can see, what does this mean? What is order of A? Order of A is the smallest integer such that A raised to n equals to identity. So what could be order of A? Suppose order of A is n. Can n be less than P? Right? If suppose n is, let us say, order of A is not 1 because A is not equals to identity, so order of A is not 1, so n is, this is not equals to 1, so it is strictly less than 1, and A raised to P is identity, so order of A must be either less than or equals to P because it is smallest. But suppose n is less than P, then n divides P. Right, from this exercise, if order of A divides the power, this A raised to m equals to identity. So here we have A raised to P equals to identity. Therefore, if order of A is n, then n raised to n divides P because A raised to P is identity. So if order is n, then n must divide this power. But n divides P, P is prime, so the only two possibilities are n equals to 1 or P. But it cannot be 1 because A is not equals to identity, so this is not possible. So that means n equals to P. N equals to P, so that is order of A equals to P. I hope this is clear. Again, I am repeating what is Cauchy's theorem. G is finite abelian group. Right now we are considering abelian case. Finite abelian group, and P is a prime dividing order of G. Then there is an element in G which is other than identity. Of course, E raised to P is identity, but there is what Cauchy's theorem says, that there is at least one element other than identity such that A raised to P is E. Now what does this mean? What could be the order of A? Suppose order of A is n, certainly it has to be less than P because already A raised to P is identity and order is the smallest integer. So, and order cannot be equals to 1 because A is not identity. Only identity has order 1. So n is less than equals to P. But then by the above exercise, that is why I have given that exercise. By that above exercise, what we can say, n divides P. But P, because P is prime, only two numbers can divide P, 1 and itself. But 1 is not the possibility because A is not equals to identity. So n must be equals to P. So that means order of A is P. Is it clear? So order of A is P. Therefore, this statement, in other words, if we want to write this, so in words, if you want to write, in other words, if let G be a finite abelian group, and P be a prime such that A raised to P be a prime such that P divides order of G, then there is an element, or we can directly say that G has an element of order P. G has an element of order P. So this is what it says. There is A belongs to G, A is not equals to identity such that A raised to P is identity. That means A is not identity, so order of A cannot be 1. A raised to P is identity. What could be order? It cannot be less than that, because if it is less than, it will divide P. If divides P, it has to be P. So that means G has an element of order P. So there is A in G such that order of A equals to P. So this means that order of A equals to, it is P. So that means if I consider a group of order 10, a group with 10 elements, we don't know what is the order. Order of element divides order of group, that much we know. So it will always have an element of order 2, because 2 is a prime dividing by Cauchy's theorem. 2 is a prime dividing the order. It always has an element of order 5. Right? Group of order 30. What are the primes dividing 30? 2, 3 and 5. So every group of order 30 has an element, at least one element of order 2, at least one element of order 3, at least one element of order 5. So Cauchy's theorem says that if a prime divides order of group, right now finite abelian group, otherwise in general, then G must have an element of order prime, that P. Right, so now finally we prove this. So we prove by induction on order of G. We prove this result by induction, principle of mathematical induction on order of G. So the first case in induction, we know induction, we take the base case. Suppose order of G equals to 1. Then the result is vacuously true. When the result is vacuously true. What do you mean by vacuously? Vacuum. Vacuum means nothing. So vacuously true, or the result is trivially true, or the result is trivial. Why this result is true? Vacuously, because there is no prime. See the theorem. What theorem says? If P divides order of G, then there is an element such that A raised to P is identity. But order of G is 1 here. There is no prime dividing. So there is nothing to prove. Whenever there is a prime dividing, we have to prove something. Here there is no prime dividing order of G, so there is nothing to prove. So this case is done. And the next comes induction hypothesis, where we assume we are proving induction on order of G. So order of G, whatever may be, but all those groups with order less than order of G, the result is true. So induction hypothesis, what it says, that suppose the result is true for all abelian groups having order. So that means suppose the result is true for all the abelian groups having whose order are in less than order of G. And now we consider 3 cases. Right? So case 1. Case 1 is that now we prove the actual case or for G, order of G. So case 1, G has no proper subgroup. That is, G has no subgroup other than no proper subgroup. So only subgroups of G. G has no subgroup other than identity and G. This is the first case. And in this case, by the exercise, that is why this exercise was given. This will be useful here. So G is a finite group. If it has no proper subgroup, then G is a cyclic group, and moreover the order of G is prime. So G is a cyclic group with a prime number of elements. And in the elements class, the prime order knows. So there are prime number of elements. So this is the case. Then so I just write here for your reference. Then by above exercise, we need not prove this in exam if Kosher's theorem is asked for abelian groups. This much you can assume, but exercise I recommend you all do this exercise. Then by above exercise, G is a cyclic group of prime order. Right? G is a cyclic group of prime order, and what we have assumed, P divides order of G. So this order of G itself is prime, so that P must be this P. So that prime must be this P, and that prime must be P, and so G is cyclic group of prime order. Since G is cyclic, it is generated by one element. G equals to A for some. It is generated by one element. So suppose A is a generator. So G equals to A for some A in G. Then we know that order of generator is same as order of the cyclic group. And order must be P, because G is cyclic group of prime order. Because G is cyclic group, so of order P, and so A is generator. So how the group is actually looks like? The group will be A square, A cube, and up to A power P minus 1. And then we take A power P, we have identity. So there are A square up to A power P minus 1. There are P elements, and that is G. So order of A is also P, and order of G is also P. So in that case, we have found an element whose order is P, and A is a generator, so A is not equals to, so thus A is A in G with A is not equals to identity, and A power P is identity. So this result is true in this case. Now we consider case 2. So this was the first case. G has no proper subgroup. Now we consider the case 2. So that means this case we consider G as a subgroup other than this 2, trivial, other than this proper subgroups. So G has a subgroup N other than G and E. So other than this 2 trivial, there is a non-trivial subgroup, a proper subgroup, and one more case is this: P divides order of N. So proper subgroup, there are 2 cases: P divides order of N, P does not divide order of N. Right? Once again, going back, we are proving by induction. If prime divides order of G, G has an element of that order P. So order of G equals to 1. There is no prime dividing this, so the result is trivial in this case. Induction hypothesis. Suppose the result is true for all those abelian groups who have this number of elements less than the number of elements in G, whose order is less than order of G. Now there are 2 cases. Actually 2 cases. One is that it has no proper subgroup, G has no proper subgroup, and another one is G has proper subgroup. No proper subgroup, by the above exercise, G must be cyclic group of prime order, and we have assumed that in the statement P divides order of G, so order of G must be prime order નું છે, prime divide કરે છે, તો કયો prime હશે? That same prime P, order of G equals to P. But because it is cyclic, it is generated by one element, let us say A. And because it is generated, so the group looks like A square up to A power P minus 1, then A power P is again this. So order of A is also P. That means A power P is identity. A is not identity, that is what we are looking for. So no proper subgroup, that case is done. Now the second case is that it has a proper subgroup, but now there are two sub cases. First one is that P divides order of n, this one, and the second one will be P does not divide order of n. So we are considering, suppose n is a proper subgroup of G and P divides order of n. But because n is proper subgroup, in this case, since n is a proper subgroup, order of n, what is order of n? Order of n is strictly less than order of G. And here we use the induction hypothesis. We have assumed the result is true for all those groups whose order is strictly less than order of G. So n is a proper subgroup, so order of n is strictly less than order of G. And here we are using this, the fact that P divides order of n. So by induction hypothesis, what we have, there is B belongs to n, because it is in n, it is in G, because n is subgroup of G, such that B is not identity and B power P equals to E. So this gives us B belongs to G. So in this case also we are done. So this case is very easy. By just induction hypothesis we can prove this case. So now the final case. I hope this is clear. Just stop the video and rewind it if you need to. And now the final case, that is again a subcase of this, but this will be G has a proper subgroup. So G has a subgroup n other than, of course it is proper, so G has a subgroup n other than G and E. And in this case, it may happen P does not divide order of n. Right? For example, if we consider G equals to order of G equals to 10, and the prime we are looking for is 5, and suppose n is a subgroup, proper subgroup of order 2, but 5 does not divide 2, neither 2 divides 5. So that kind of case may happen. So then we cannot use induction hypothesis in this case. So P does not divide order of n. So this is the case we are in, and this is the non-trivial case. Other two cases were trivial, not that difficult. Right? So G has a proper subgroup, and P does not divide order of that proper subgroup. So then some work has to be done. This is the last case. So since G is abelian, we know that subgroup of abelian group are all subgroups are normal. So since G is abelian, n is a normal. N is normal subgroup of G, and if n is normal subgroup of G, so G quotient n is a group. G quotient n is a group. We have seen if and only if n is normal. N is normal here, of course, because we are in the abelian case. Here is where we use the abelian case. So n is normal, and if n is normal, G quotient n is a group. And what is order of G quotient n? Order of G quotient n is, we know this is order of G upon order of n. Right? This is order of G upon, so let me write like this, order of G upon order of n. But what we have is, but P divides order of G. This is in the statement of Cauchy's theorem. P divides order of G. And by this case, what we have considered this case, P does not divide order of n. It is not dividing order of n, but it divides order of G. That means P divides the numerator. Here there is P dividing this, but P is not dividing this denominator, as you can see here. P divides the numerator, P does not divide the denominator. So P does not cancel out. If it divides numerator and denominator, then it may cancel out, but it is not going to get cancelled out because it is not dividing the numerator. In this case, P does not divide order of n. So that means, so thus, then hence we can write P divides order of G upon order of n, because there is a prime dividing the numerator as a factor of the numerator, but it does not divide denominator. So that is P divides order of G quotient n. P divides order of G quotient n, and since G is abelian, G quotient n is also abelian. Right? This quotient subgroup is also abelian because G is abelian. And what about order of G quotient n? It is strictly less than order of G, because n is a proper subgroup. Because it is proper subgroup, order of G upon order of n is strictly less than order of G. So G quotient n, see now we are coming to the hypothesis, induction hypothesis. G quotient n is an abelian group. P divides order of G quotient n, and the order of G quotient n is less than order of G. So that is actually Cauchy's theorem. We have assumed the result is true for a hypothesis of this. So we have assumed that the result is true for all those abelian groups with order strictly less than order of G. So G quotient n is an abelian group. P divides this, and order is strictly less than order of G. So then by induction hypothesis, there is an element in G quotient n, not in G. G quotient n માં આવી ગયા ને આપણે, and then from this element we will again go back to G. So by induction hypothesis, there is an element x in G quotient n such that x is not equals to e. Identity આની શું આવે? X is not equals to e. That means x is not equals to n, and x power p equals to identity. That means x power p equals to ne, which is n. બરાબર? કોશિશ થિયરમ વાપર્યો આપણે, પણ શેમાં વાપર્યો? ઇન્ડક્શન હાઇપોથેસિસ વાપર્યો ને. ઓર્ડર ઓફ G quotient n is strictly less than order of G, અને જો પ્રાઇમ ડિવાઇડ કરે છે, in this case p divides order of G quotient n. So, and G quotient n is abelian. So it is a finite abelian group. P divides order of G quotient n less than having order of G. So the theorem applies. So there is an element x in G quotient n which is not identity. That means x is not equals to n. N is the identity of this, and x power p equals to n. But x belongs to G quotient n means what? X belongs to G quotient n. X belongs to G quotient n. This implies x equals to nb for some b in G. G quotient n elements keva hoy? They are the cossets. So suppose x is some right cosset, and x not equals to n. X not equals to n means x is not equals to n. This implies nb is not equals to n. This implies b does not belongs to n. So what we are using here is right. So this is the fact we are using, that x is not equals to n. That means nb, x is equals to nb. nb n ના હોય એનો મતલબ કે b n ની અંદર ના આવે. So this is the one point we are getting from here. Another point is what? From this, x power p is n. X power p equals to n. This implies, આનો મતલબ શું થાય? X is what? nb. So nb power p equals to n. nb power p. What is nb power p? nb, right? na nb આનો પ્રોડક્ટ શું થાય તો કે nab. So nb square શું થાય તો કે it is nb, that will be nb square. So nb power p શું થશે? nb p times. So this implies n and then b power p equals to n. આનો મીનિંગ શું થાય? b power p belongs to n. આ જો કોસેટ n થઈ જાય આઈડેન્ટિટી nb power p, એનો મતલબ કે this element must belong to this n. So b power n from this x power p equals to identity. That means nb power p is identity, which is nb. So nb power p, that is identity. And if this is identity, then this element b power p must belong to n. So b does not belong to n and b power p belongs to. So these are the two things we have obtained. One is b does not belong to n and b power p belongs to n. This is what we obtain, right? So b power p belongs to n. So by corollary of Lagrange's theorem, then by a corollary of Lagrange's theorem, we have, which was a corollary. So I am writing the corollary here. So a belongs to g and g is finite. A power order of g, the last corollary probably we proved, a power order of g શું થશે? Identity that. This is the one which we are using. So b power p belongs to n. b power p belongs to n. That means b power p raised to order of n. શું થવું જોઈએ? This must be identity. Is it clear? b power p raised to order of n is identity. That is b power order of n. We can write like this also. b power order of n raised to p. This is identity. Right? This case is non-trivial. Let us, before proceeding further, let us consider this case again. So G has a proper subgroup n. So it is different from G and E because it is proper. And in this case, P does not divide order of n. હવે આમાં quotientમાં જવું પડશે. So G is abelian. So every subgroup is normal because abelian group છે Gx G inverse. So x થવાનું છે. So it is normal. So G quotient n, because it is normal, quotient layer, so that is a quotient group. G quotient n is a group. And G quotient n, what is the order? Order of G upon order of n. This is proper subgroup. Therefore, this is strictly less than order of G. હવે P divides the numerator by Cauchy's theorem. જે આપણે સ્ટેટમેન્ટમાં આપેલું છે P divides order of G. અને આ કેસમાં એઝ્યુમ કરેલું છે P does not divide order of n. So P divides numerator, P does not divide denominator. Therefore, P divides the quotient. Order of G upon order of n. That means P divides order of G quotient n. G is abelian, G quotient n is also abelian. P divides order of G quotient n. And order is strictly less than order of G. So by induction hypothesis, we assume the result is true for all groups, abelian groups with order strictly less than order of G. So by this, G quotient n ni under element hase, which is not identity, that is not n, and x power p equals to n. Right? But G quotient n no element as x, that means x is equals to nb. It is some coset for some b in G. And now we use these two facts. X is not equals to identity. This means what? X is not equals to n. That means nb is not equals to n. That means b is not in n. That is the first thing. Now x power p equals to n. X power p equals to n. That means nb power p equals to n. But nb is a coset. So nb p times. So you can write that n b p times. So n b power p equals to n. And if n b power p equals to n, that means this b power p must belong to n. So b power p belongs to n. Then we use the corollary of Lagrange's theorem, which says that if A is an element of this group G, then A power order of G equals to identity. Because b power p belongs to n, b power p raised to order of n is identity. બરાબર? જે ગ્રુપમાં આવતું હોય એ ગ્રુપનો ઓર્ડરનો પાવર લઈએ So we get identity. So b power p raised to order of n, this is identity, and therefore b power order of n raised to p is identity. પણ હવે આ તો બધું g quotient n માં ચાલે છે. Now we want to go back to g from g quotient n. So this is the element which we are looking for, and this is so take c equals to this one. Take this as c. Take c as b power order of n. Right? This is the element which we are taking. B belongs to G. So b power order of 1. B. How many times? Order of n times. This belongs to G. This is the one which we are looking for. Right? C equals to this. This is the element which we are looking for. And so C belongs to G. And what is a property then? C power P is this is C. B power order of n is C. So C power P is identity. So first thing is already done. We wanted to find an element in G. We wanted to find an A in G. Sorry, we wanted to find an A in G such that here A in G such that A is not identity and A power P is identity. So we have found C such that C power P is identity, but only thing which remains to show that C is not identity. So we have found C such that C power P is identity, C is in G. So it remains to show that C is not equals to identity. So this is the remaining part, right? And yeah, what we here we got x belongs to G quotient n. X is not identity and x power p is n. X power p n થાય and p is prime. So that means what? This implies that order of x is p, right? So this implies order of x is p. Why it implies order of x is p? X identity નથી, so order is greater than 1 and the smallest integer, but x power p equals to n થાય છે identity. So the smallest integer also must be prime, because again પહેલા જેવી જ વસ્તુ આપણે જે કર્યું, suppose order is n અને x power p identity થાય છે, therefore n must divide p, પણ p prime છે તો n equals to either 1 or p. 1 તો થશે નહીં because x is not identity, so 1 નહીં થાય તો p થશે. That means this also we should keep in mind, that order of x is p, right? So order of x order of x is p. That is what we have. And now we have to show that C is not equals to identity. So suppose C equals to identity. So C equals to identity. This implies what? C is this b power order of n. This is identity. If b power order of n is identity, take this coset n b power order of n. This equals to ne, which is n. But what is n b power order of n? This is nb, how many times? Order of n times. So this is nb, this coset times order of n equals to n. But that means x power order of n is n, ne equals to n. X power order of n is this. Okay, so x power order of n is identity and order of x શું હતો? Order of x was p. બે વસ્તુ હતી. X power of order of n is identity, order of x is p. So what is the relation by that exercise? By exercise 2. Since order of x equals to p, This is just for our reference by exercise 2. P divides, what should P divide? P divides this power, P divides order of n, which is a contradiction. Why this is a contradiction? Because our assumption, આ કેસમાં આપણે એવું લીધું હતું, P does not divide order of n. This was our case. Right? This was our case, P does not divide order of n, but here we have got x power P, order of x is P, and x power order of n also identity આવ્યું, so P divides order of n, which is a contradiction to our assumption that P does not divide order of n in this case. Right? So in this case we had assumed P does not divide order of n, so it is contradiction. Therefore, so assume કર્યું હતું આપણે, we have assumed that C equals to E. This was our assumption. So C is not equals to E. Therefore C is not equals to E. And since C power P is identity, C is not equals to E, the theorem follows. This is what we wanted to find. Right, so once again quickly revising all the cases. You can stop the video at this point if you have understood the proof. So G is a finite abelian group, P divides order of G, then there is an element in G of order P. We prove by induction, order of G is 1, there is no prime dividing order of G, nothing to prove. Induction hypothesis, suppose the result is true for all groups whose order is less than order of G. Assume this. Now case 1, G has no proper subgroup. By first exercise, G must be a cyclic group of prime order. Statement એવું છે P divides order of G, and order of G is prime, તો પછી કયો prime હોય? Same prime. So order of G is P. Not only that, cyclic છે એટલે order of A is also P, where A is a generator of P. A is a generator of G. So order of A is P. That is what we wanted. A is not equals to identity. A raised to P is identity. Second case, G has a proper subgroup. પહેલામાં proper subgroup નહોતું. In this case, we have a proper subgroup, but P divides order of n. Because it is proper, order is less than order of G. P divides order of n. By induction hypothesis, there is an element B in n, such that B is not identity, but B power P equals to E. But as soon as we get B in n, B is in G, because n is subgroup of G. So in this case, we are done. Now this is one non-trivial case. Proper subgroup other than, so proper subgroup, so that means n is a subgroup other than G and E, and in this case P does not divide order of n. Order of n ને divide નથી કરતું. આ કેસમાં quotientમાં જવું પડશે, quotientમાંથી element મળશે by applying theorem, and from that element we go back to G. So because G is abelian, n is normal, so here we use the case it is abelian. This case we are using here abelian. So n is normal, G quotient n is a group. Order of G quotient n will be order of G upon order of n. Because n is proper subgroup, this is strictly less than order of G. And P divides order of G, that is given in the statement of Cauchy's theorem. P divides order of G. And આ કેસમાં લીધું, in this case we have taken P does not divide order of n. That means P divides numerator but not denominator. Therefore P divides order of G quotient n. G quotient n is also abelian because G is abelian. So by induction hypothesis, because it has order less than order of G, by induction hypothesis there is an element x which is not identity. Identity of G quotient n is n. So x is not equals to n, and x power P equals to n. Then what must be order of x? Smallest integer. So P થી નાનો હશે, so less than or equals to P. Order of x is, say, let us say m. M is less than or equals to P, but by that exercise m divides P. So m equals to 1 or P, because P is prime. 1 though is not possible because x is not identity. So m must be p. So therefore order of x is p. That is our first conclusion. We are going to get contradiction here. Now this is the thing. X is in G quotient n, so x is some coset nb for some b in G. Now x is not identity, that means nb is not equals to n, that means b is not in n. Again x power p is identity n, so x power p is n, that means nb power p is n, that means nb p times. So n b power p is n, that means b power p is an element of n. So b power p is an element of n, which is again an element of G. Okay, but now we use the corollary of Lagrange's theorem. If A is an element of G, A raised to order of G is identity. B power n is an element of n. So B power p is an element of n. So B power p raised to order of this group, it's an element of n. So raised to order of n is identity. That is just exchange the power. B power order of n power p is identity, and this is the element which we are looking for in G. So call C equals to B power order of p. Then automatically we get C power p is identity. One thing we get from this above itself, C power p is identity. Only thing it remains to show that C is not identity. Suppose C is identity, that means C is what? B power order n is identity. Take the coset both sides. So n b power order n equals to ne equals to n. But n b power order of n equals to nb. How many times? Order of n times. So nb raised to order of n equals to identity. Nb is nothing but x. So x raised to order of n equals to identity n. That is identity of G quotient n. This is identity of G quotient n. So x raised to something is identity, and order of x is p. By exercise 2, the order must divide this power. So p must divide order of n. So p must divide order of n, and this is where we draw a contradiction. Because we have assumed in this case p does not divide order of n. So here we are getting the contradiction. And so our assumption that C equals to E, this must be false, and therefore C is not equals to E. C power p is already identity, and therefore this completes the proof of the theorem, and this completes the unit 1, which again we'll discuss tomorrow in the Google Meet. We're going to discuss this theorem. This video is well in advance. If you do not get time to watch this in advance, then watch it afterwards if you need to revise. So if G is a group of order 24, what are the primes dividing 24? 2 and 3. So G has an element of order 2, G has at least one element of order 3. We don't know whether it has an element of order 4, 8, that we don't know, but G has an element of order 2. જે prime divide કરતો હોય એ ઓર્ડરનું તો એલિમેન્ટ મળે છે. This is going to be very important theorem, especially in problem solving. With this I stop here, and this completes unit 1. See you tomorrow.